Otherwise, we're going to get started with asymptotic analysis. Who's familiar with asymptotic analysis? Raise your hands. Okay. Are people not raising their hands because they don't know about it at all, or they're not familiar with it? Right? I'm sure that you must have seen this in a less formal treatment in various other contexts, but today we're going to be talking about it mathematically, and today we'll be proving it. Okay? We're not going to just eyeball our code and say, oh yeah, it looks like O of n, and really loops forever. Okay? We're going to actually prove that our code terminates, and then also terminates within a predictable bound. Okay? Actually, we've already been proving our code terminates by proving totality. But, okay, so asymptotic analysis, let's get started. So 3 things for you today. We're going to talk about asymptotic complexity in generality. We're going to talk about the theory behind big O notation. It's probably going to be a review for some of you. Then we're going to talk about this idea of work and recurrences, which are how we quantify and solve for the runtime cost of a function. And then we're going to talk about parallelism, which is a really hot topic with functional programming. But that will be our schedule for today. All right. So I got into the habit of putting these last time slides, and then I realized that it was only helpful when the last lecture was relevant to the next one, and that's not true. So I'm not going to talk about this, but that's what we did last time. Cool? All right. So far, we've been doing programming. We've been doing functional programming, but that's mostly what we've been doing. We've been doing some coding and then proving some stuff about our code, but now we want to move on to some other stuff. So today will be very little coding, but we'll be analyzing our code that we have written, and plus or minus a few new functions. Okay? So we've learned about a bunch of things like data type declarations, pattern matching, and whatever. But I promised to you on the first day that functional programming was a better kind of communicating. Okay? But that's not the only thing we care about. We don't just care about communication. We care about how our code runs. Right? Okay, never let it be said that performance concerns went out the window. They went halfway out the window. We defenestrated them halfway. Okay? So we're going to talk about how our code performs. And this iMovie thing is really annoying me right now. Hold on. Whoa. Whoa. What is that? Oh, you have to click on them in a prescribed order. I see. Right. Okay, thank you. Cool. Okay, let's move on. Okay. So we're talking about performance, but performance is a hard thing to measure. So far, we've been talking about performance in terms of steps made by a computer. If I have 1 plus 2 minus 3 plus 4, we say this takes a step to 3 minus, well, I don't need the parens. 3 minus 3 plus 4, right? And then this steps to 3 minus 7, steps to negative 4, right? This is our idea of what it means to take a step in computation, what it means to measure the cost. But this is not exactly super representative, because what does a step mean? And when I think about this, I'm reminded of a thing that happened to me, very formative experience, when I was in first grade, and I was in gym class. And my gym teacher asked this kid named Joseph and this girl named Grayson to go and walk 10 steps. And then Joseph walks, and he walks like this. And then he walks 10 steps, and then Grayson walks 10 steps, and she's behind him. And then my gym teacher was like, see, people's legs have different lengths. And that means they cover different distances when they take a step. This is all to say that a step is not always a step, right? On different machines, on different hardwares, depending on whether or not the computer woke up on the right side of the bed, it can do wildly different things with its performance. And that's not so nice, right? I want to be agnostic to hardware details. I want to be agnostic to implementation details of the computer. That doesn't mean I don't believe in them. That means I don't care about them. Okay? So we're going to be ignoring all this stuff because we care about analyzing performance mathematically. Okay? And where does that come in? Well, we get big O notation. I'm sure some of you know, but in the limit of data, we're interested in how much time it takes to do something. Because if I'm throwing petabytes of data because I work for Facebook or something into my machine learning advertising networks, I want to be sure that it will perform well when it has to read in said petabytes of data. But I don't care so much when I need it to render like a 1 MB JPEG on my computer. Okay? So we're interested in the limit of computation, the limit of performance. Right? And this should be a fairly familiar concept to some of you. But big O notation is how we measure that in the limit of the size of the input. And there's some mathematical details that are pertinent here that I have to stress. Okay? But we're talking about big O notation to describe a function. A general function I have, f, I'm trying to use big O notation to describe it. And I'll quantify that here. So formally, if I have a function f of type naturals to naturals, let's say, okay, the positive naturals, this is describing the cost. Like it's saying, okay, on an input of size 2, then this is equal to like 3, and that means steps. It means like abstract units on some computer that I don't care about. But that's what this function means. This function is denoting that cost abstractly. Okay? Don't forget about this function because that's where we start. So once we have that function, what we're doing, okay, so yeah, the input is some metric of the data input. Okay? Like I have to be able to quantify what it means for the input to grow. And we're going to see that this takes multiple forms depending on what our data looks like. For now, let's think about like functions on numbers because those have a clear size metric, which is the size of the number. Okay. All right. There's the definition. So I'm going to not write that for you. We say that this function f is in, like in set theoretically, in O of g, if for that function g there exists n sub 0 and c such that for all n greater than equal to that same n0, f of n is less than or equal to c g of n. I'm going to let you write that down for a second, and then I'm going to explain what the hell that means. Okay? Because it's not super nice to look at. But the point is, we can instantiate these constants such that for all things greater than n naught. Okay? I'm going to continue let you writing that down for a second here. But how many people have seen this definition before somewhere? Cool. Okay. How many people feel really cool with it, like really strong, like you know exactly what it means? Great. That's why I'm here. Okay. What does it mean? Okay. What this means is a runtime function f, my function which describes my performance, is in this complexity class O of g, such as O of n squared or O of n, if that means that there is a point on the function beyond which the performance of my runtime function, my performance function, there's a point beyond which my function is always less than the O of g function, like the n squared. Okay? There's always a point by which it is smaller. So at this point, my performance function f is always smaller, provided that I also get the chance to scale up the complexity class function by a constant amount. And I have pictures, so I will show you in a second here. Okay? I explain this better on the next slide, so I'm going to talk about this. Okay. Why are n and n not important? Here's why. I've got two functions for you here, g of n and f of n. They're n and 2n, respectively. Okay? If we restrict our attention to the positive naturals, here on this function for n and 2n, f is always less than g. So it's a fair bet to say f is in O of 2n, right? But what if I shift it up by 1? What if I make f of n instead n plus 0.5? Shouldn't we be able to say that n plus 0.5 is also in O of g of n? But I can't because here, look at this. F is not always less than g. There is a point at which f is no longer less than g. But I don't care about that point because from here on out, it's smooth sailing. F is always less. So I care to say that this point right here, this intercept between the two functions is my n naught. It's my n0 such that everywhere to the right of it, I'm always less. Does that make sense as to why we need n and n naught? I'm trying to offset this constant factor. Okay. Well, I didn't see any nods, but no one said anything. But this is the picture you should envision in your head when we're trying to understand why this is important. Okay? So I explained to you n and n naught, but what about c? So here's why c is important. I've got f of n is equal to n, and g of n is equal to 0.5 of n. And we see here that f is always greater than g. But we want to be able to say that 0.5 of n is in O of n. Right? 0.5 of n is a linear function. I should be able to say that they're in the same complexity class. But I can't because guess what? I can't say that f is in O of g of n, sorry. But I can't because it's always greater somehow. Because g of n got the advantage in terms of a constant factor, a constant multiplicative factor. But if we scale g of n by 3, instead we take it from 0.5n to 3 times 0.5n, now f is always less. So the point I'm trying to get across here is that n and n naught, this idea of always smaller after a point, is to get us past constant additive factors, in a sense. Okay? And then this idea of being able to do it modulo constant factor scaling, this is because I want to be able to say that I'm, for things that like have roughly the same asymptotic behavior, you're not going to get the lead on me just because you have a constant factor in front of you. Okay? Like things that are both approximately linear will be able to obey this relation as well. Does that make sense to everyone? I'm trying to paint this picture in your head. Okay. All right. So we're going to move on because I have a lot to talk about today. Cool. Okay, in this class, generally, and in general, honestly, time complexity only falls into a few buckets that matter. So here's the hierarchy for you, all right? We have O of 1 is less than, strictly, O of log n, is less than O of n, is less than O of n log n, is less than O of n squared, is less than O of n cubed, so on and so forth. And there's a few buckets in between I'm missing that I don't care about. Okay, but these are the ones we mainly care about. And in this class, we will pretty much only ever see up until O of n squared. But we will see everything up until O of n squared. Okay, so if you're taking the midterm, all right, and you're like, I have no idea what the complexity of this is, don't guess O of n to the 4. All right, guess one of these. All right, you'll get it. By the way, that's not good advice because we grade you on showing your work. So don't do that either. All right, you won't get points. But in this class, we're going to see just that. And this in is more permissive than we need because we want something called a tight upper bound. That is to say that O of 1 is also in O of n. And O of 1, or any function that is like constant, right? I don't mean O of 1. I mean a function like f of x equals 2. Okay, that is in O of n. It's also in O of n squared. It's also in blah, 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 blah. Okay? But we want, if a function falls somewhere here, we want the one that's most to the left, the least complexity class that it falls into. Does that make sense? And if you don't get it approximately tight, that we will be sad. All right? Cool. Okay. Oh, yeah, that was the sentence where I talk about it. We want a tight asymptotic bound is what we say. Okay? Okay, here's some common things, ways that you can think about each complexity class. Like you should, at a certain point, you should have like a hash table in your mind where you see like a bound and you're like, oh yeah, that's like blah, 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 blah. I said hash table. Whoops. So O of 1, for instance, who laughed? If I say O of 1, that's the cost of, say, like consing an element onto a list. That's an O of 1 operation. Also multiplying two numbers. If you're an ECE, I don't want to hear it. Also stepping an expression once. Any one step is a constant amount of work. Okay? And then O of log n is how much time it takes to binary search an interval that's like n wide, finding an element in a binary search tree of n nodes, so on and so forth. Okay? So you should always think like weird like binary recursive stuff when you see O of log n. Okay, that's the only way O of log n ever gets introduced. O of n, length of a list, last element of a list, so on and so forth. N log n, merge sort and quick sort. Merge sort we will see next lecture, and I promise you, I said this in my alpha series, but next lecture I promise you we will implement merge sort in 15 lines, generously spaced. Okay. And it will be one of the crowning achievements of what we can do with functional programming. It's going to be really cool. Okay? But we will see it later. And then n squared, insertion sort, selection sort, doing naive stuff when you should have done something better and gotten an O of n bound, okay? Which happens often. And we'll actually see an example of that today. Okay? So just to build your intuition, these are reasons why you should see these bounds. Okay? These are our use cases. All right? Cool. Oh, yeah, I want you to not forget about the function, basically. Like if I write to you an SML function, okay, that function has a mathematical function that describes its runtime behavior. What we're doing is we want to solve for that function. We want to find what that function is and then classify the complexity. But don't forget about the function that exists. I feel like most people probably go from code to bound, right? But in most cases, what's happening here is that the code has an invisible, like some underlying function that we maybe can't compute, but like exists, right? There is a function that describes its runtime behavior, its performance. And you use this to get to the bound. That's the point. Sorry. You use that function to get to the bound. So don't forget about this function, because it's what we're going to be solving for here. OK? OK. I should also tell you that it's important what the function takes in. So I said that this is true, right? F is from the positive naturals to the positive naturals. But we have to define what that means. If I have an SML function that takes in a tuple of two things, what does this mean? What is my input size? And we're going to find that we have to define that. So when we're going to be doing our analysis, I want you to first think, what is the size metric I'm interested in? OK? That's going to be important. And I realize I'm talking abstractly. We'll concretize in 2 slides. All right? OK. And yeah, we've been doing this very implicitly up until now. But now we'll do it explicitly. All right? OK. Working recurrences, let's talk about it. So big O is useful, but it's not so useful if we can't actually get at that function I was telling you about. So let's do it. So let's have this length function. All right? With the length function, we're tempted to be like, oh, it's O of n. Why? Because we look at every single element in the list. And like that's good enough reasoning for 122 or 112, but not for us. Okay? We want to be able to assure ourselves this is true. And we're going to be able to do that by computing something called a recurrence. A recurrence is a recurring way, a recursive way of categorizing how much work is done by this. Work is basically what I'm using to determine or to denote the amount of runtime cost. Okay, I have a few slides later where I define it. But let's do it. So here's what we're going to do. I'm going to do this for you right here, and I'm going to show you the general form. All right. For the fact function, the length function, I have two cases: base case, recursive case. So my recurrence will have two cases. It's a piecewise function. I'm going to start with this. I'm going to say W is my work function. Okay. W sub fact. I keep saying fact. W sub length. And I'm going to take in 0 as my base case. And I want you to not forget that this is my size metric. And what I should do is I should say my size metric is the size of the input number. Okay? I should have probably put that above. But the point is that this is what that is. This is my size metric. And this is my function name. All right? I'm defining a recurrence on a particular function. All right? And what is W sub length of 0? Well, I'm tempted to say this. I'm tempted to say it's 1, right? Because it takes one step to reduce to 0, right? That makes sense? Except that this function from end to end we're talking about is in abstract units. Like my computer might take longer to do something on a different day than it did today, right? I'm talking about real cost. So here's what we're going to write. We're going to write C sub 0. It is an unknown constant. I don't know what it is. I know it exists. And I know that it doesn't depend on my input. Okay? So I'm going to say that the amount of work, and you might also be thinking, I didn't do anything, right? I just returned 0. But there's time cost associated to returning a number, to returning from a function call, to calling the function in the first place. So no matter what you do, pretty much, no matter whatever you do, there's always a constant factor left. All right? I'm looking at this side of the room a lot. I'm neglecting you. Sorry. So don't leave out this constant. All right? And then we're going to find what? W sub length. Now let's do the next case, right? It doesn't suffice to do it when my input is 0. I want to be able to define my recurrence when I have an unlimited input. So W sub length of n is what? Well, what do? We call ourselves recursively on an input of size n minus 1. Oh, geez. Oops, sorry. I was in my fact brain. I was like, fact takes in a number. No, it's actually a list, sorry. But here I'm going to define my size metric as the length of the list. So that makes sense. I kind of had to context switch there. But basically, to get a number out of my input, I'm talking about the length of the list. So I'm saying a length on my recurrence on a list of length of 0 does C sub not work. And then I'm saying my recurrence on my function takes time on a list of length n. It takes what? So we call ourselves recursively on a list of length n minus 1 because x has 1 less length. So we'll say it's W sub length of n minus 1. But I'm not done here, because I had to do some work after. I did that, and then I added a number. And addition, as I told you earlier, is constant time. So we're going to say plus C sub 1, not C sub 0, because these are different constants, right? The cost of doing this is a constant, yes, but it's not necessarily the same constant as this. Does that make sense to everyone? OK. So we're going to define this recurrence, and then we'll solve. OK? What the heck? Oh, here it is. So we define the recurrence, and then we solve. So let's go forward. Blah, 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 recurrence relation. Oh, yeah. OK. I probably should have told you this. But yeah, a recurrence relation is two or more mathematical equations that describe the cost that we have. All right? If you want to copy that in definition, you can. I kind of told it to you out loud anyways. And this is used to describe the work, which is the runtime cost. Sorry. I'll give you a second. But we're going to solve this next. And the method that we're going to use to solve this is called unrolling, which means just step the mathematical expression, this one, until you find a pattern. OK? Go until you find a pattern, and then get a closed form. And once we have the closed form, which is to say that we have an expression that doesn't depend on W sub length anymore, once we have that, then we can estimate a bound. Okay? And I'm going to show you how we do it here. Okay? So maybe I'll have enough room to do it. Let's do it. So I want to solve for the general closed form of W sub length on n. Okay? We know by this definition It's W sub length of n minus 1 plus C sub 1. And I know, because of this, right, it's another call, right, except now n is n minus 1. So I'm going to call W sub length, and I'm going to get it W sub length n minus 2 plus C sub 1 plus C sub 1, right? And then if I did it again, I'd get another C sub 1, right? So you can see every time I call W sub length, I get a C sub 1 out. So if I wanted to equals dot 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 this, I would say this eventually goes to the sum from I equals 0 to n of C sub 1, and then eventually we reach the base case. So we get C sub 0. Okay? So I know that I've told you when you're proving things, don't use ellipsis like dot 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 and then notation. Here it's OK. Here, when we're doing unrolling, it's OK to say, oh, eventually this goes to that. And then we have an ability to get a tight bound. Let me use this word now. Right? So once we have this, yeah, I should have moved words. Once we have this, then what is this? This is just n multiplied by C sub 1, right? Because if I add it to itself n times. So we have that's equal to n C sub 1 plus C naught. And this is just a function, right? This is a function in n. I'm saying that the cost of running length is going to be n abstract units, where one of them is C sub 1, and then one of them is C naught. So this is in O of n. This is how we're going to quasi-rigorously show that length is in O of n. Does this make sense to everyone? Yeah. I will require no justification from you that that's true. Like, if we look at the code here, like it's because we're taking every time that we generate a C sub 1, what's happening is that we get a number and we add it to 1. I would be fine if you were just like, yeah, that is the same concept, because if we're assuming that the amount of time it takes to add those numbers is not dependent on the size of the number, then it should be like roughly the same concept. We're still talking in abstract units, so like, you know, addition could take a different number of milliseconds on your machine, but in this case we don't care. So it's OK to say the same C sub 1 here.
So in terms of summation, why is the summation start from 0 instead of 1?
I mean, OK, yeah. So we generally don't care. Like if you're in approximately the right ballpark, I didn't bother to count out how many there were, but if you're off by 1, it's OK. Like the general point is that there's approximately n of them. And honestly, it'll make your life harder if you have to then go like n minus 1 C sub 1 plus C naught. Like the point of unrolling is, oh, there's a pattern here. There's roughly linear. And like honestly, we're not going to let you jump immediately to here, but you should show like, OK, there's like it might even be better to say this. But there's people that will have notational concerns over this, so I prefer not. Yeah.
Can I like assert the closed form and then prove it, and then will that also be valid?
Assert the closed. So you're going to state, oh, this is in blah blah blah. Here's how.
Yeah, like I assert like the closed form is n equals 1 plus C naught, and then I prove that it satisfies the recurrence.
I would be fine with that as long as you show eventually you get there. Yeah. I mean, this is extra writing on you. Yeah. Person who asked the question before, I'm giving you IG, by the way. Oh, he's not looking. That's all right. OK, cool. So we're going to do O of n. OK? All right. Blah, 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 blah. Oh, now we're going to do fact. OK, I see what happens. OK, cool. Fact is going to be a very similar case, right? If I have my base case, I do a constant amount of work. Pretty much every recurrence you ever see in your life is going to be of the form W sub f0 is equal to C naught, OK? Like, I get tired of writing this at a certain point. You should, and you have to. But there's pretty much no way for this not to be true, OK? So here's what we're going to get. We're going to get that the work of fact on input size 0 is going to be C naught. And then in the recursive case, same deal. I make a recursive call, and I do a constant amount of work. So I have C sub 1 plus, sorry. That should be a plus. C sub 1 plus the work of fact on n minus 1. Fair enough? It should look like your code. And it's almost like your code resembles the proof and your code resembles the recurrence relation. Okay? There's a theme here. I'm going for something. Okay? And this will solve out to be the same thing pretty much. Okay? I'm not going to step through the work with you. I will occasionally do that where I will say, like, we get to something which looks like W sub f of n is equal to C sub 1 plus W sub f n minus 1. If I feel like it, I'll work through it with you. But just know that this does evaluate to O of n. And no, on your tests, if you see this, you cannot immediately say it's O of n. You have to solve it out. OK? It's on your homework too. Yeah.
Are you saying it's C1 times
I made a misstep. Sorry, I am corrected it aloud, but not on the presentation. Yeah.
So do we not care about the actual abstract cost of C0 or C1?
No, it's something. It's something, and then it varies depending on your machine's state of being, whether or not you've played Minecraft recently. Like, it depends. But yeah, it doesn't really matter. Any other questions on this? Cool. All right. I suspect I'm going to have to erase this board for the next part. Okay, so this is how we set up and solve a recurrence relation, and I'm going to talk about. Oh yeah. Okay, so this is just how I solve for it, and it's fine. Where I tell you about unrolling. Wait. Okay. Cool. Okay. The next example I wanted to talk about was this find first even function. Okay. Fact is pretty simple, right? Length is pretty simple. You just make the recursive call and you do the thing. But what about if I had a function, this function, that, as the name describes, finds the first even number in a list, right? And you should be able to assure yourself this is what it does, right? We look at it. If there's nothing, we'd return none, the handy option that we learned about last lecture. And then if our first thing is even, then we return it. Otherwise, we recurse. Fair enough. How do we analyze the runtime cost of this guy? Because if we're really, really lucky, if we cross our stars and hope to die, okay, our first element is going to be even. At which point we're okay. We'd return. No big deal. But that's not always going to be the case. So would it be okay for me to be like, yeah, I'm going to hand you this function. Trust me, it's O of 1. Trust me, it's O of 1. Don't worry about it. Constant time. And then I pass it to someone, and then my NSA contractor that's taken in this function decides to pass in the petabytes of data they have on all of us in the form of a list, and then they loop for like 3 years. And they're like, what's up? Well, why do you do that? It's because we weren't pessimistic enough. Here's another life lesson to you. Be pessimistic, okay? So we're going to that sounded better in my head. How are we going to write this recurrence? Well, okay, I already talked about the length of the list, but the okay, let me not speed past this too fast. Sorry. In the base case, we're returning C sub 0 again, right? Because we just return none. But how do I do the recursive case? Because the recursive case has a branch, right? When I said pessimism, I mean worst case behavior. You've probably heard this term before. We're interested in pessimistically the worst possible performance our function can have depending on the input passed to it. Because we're not always in control of what that input is. A nefarious actor might decide to pass in something to us and then try to make our function loop. Okay, they might do a SQL injection. They might do some kind of attack on us. Okay, security stuff. I work for a security company. All right, so here's what we're going to do. We're going to be talking about worst case behavior. So what is, geez, I put the function away. But what is the worst case behavior? It's when there is no even element. I have to look at the end of the list. So let's do it up here. So we're going to do, so W sub find first even on 0 is equal to C naught. And then W sub find first even on any arbitrary input. In the worst case, I go into, I keep putting it away. In the worst case, I always enter this case, in which case I do W sub find first even work on n minus 1, where n is the length of the list. Actually, I should put this up here. Where is the length of the input? And you should preface your recurrences with this wherever you do it. But where n is the length of the input, I'm going to call it on a list of length n minus 1. Okay? And now do I call it? Am I done? I see heads shaking. Why? Actually, here's a better question, actually. If I solve this out, what is this going to be? I solve out this equation. What do I get for W sub find first even? I get C naught. I always return my recursive call. Some of you may be familiar with this, having done the induction homework, right? If you don't do anything, if you never make a recursive step, you're just going to return your base case. You got to do something, right? So plus C sub 1. It takes some work to go and fetch it, to go and return it, to go and hold it in your hand, okay, the result. All right? And then this is going to be equal to, we expand this out, we get a C sub 1 per call, dot, 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 in O of n. Yes? Yeah, I was mostly appealing to your intuition that we'd be in this case and do nothing, but you're absolutely correct. We would actually, prior to that, have to do some work to even get into the case. We have to do the comparison. Yeah, computers aren't magic. The earlier you learn the computers aren't magic and they have to do something, is better for you, I think. Yeah. Yes, if you have a multiple amounts of work, I highly recommend you don't try to write them out into different constants. Flatten them into one constant. Yep, that's good. Cool. And again, like this is probably the least rigorous part of the course. Well, yeah, this is probably the least rigorous part of the course. So like if you omit some things, as long as you do the work, right? As long as you actually show that you know how to, firstly, manufacture these recurrences, and then secondly, solve them, then we're okay. But coding details like those constants or like, other things like that, like it's okay. All right. I believe I have, yes. Okay, so I already walked you through pretty much all this stuff, right? Cool. Okay, here's the next thing I wanted to tell you about. Okay, I'm going to give you the formula for how to do this from now on. All right. So, if I want to be able to solve the general form of the asymptotic complexity of a function, if I have this function f, this SML function f, here's what I do. First thing, identify the size parameter. I set it here. Write it down. Where n is the input size of the length of the input, or n is the value of the input if we're taking in an int, or n is anything else depending on what the input is. It could be a tuple, it could be a function, which is strange. It could be a lot of things, okay? But identify what this is and then state it explicitly, all right? And we're going to see a couple examples where that's not true. Then write the recurrence. The recurrence will usually be multiple branches, okay? I've got my base case and I've got my recursive case. You might even find that you have multiple depending on how your code looks, okay? The recurrence follows the code. The code gives us the recurrence. But we start from the code, okay? And then write these equations in the worst case, and then simplify the recurrence. Solve the recurrence. Do this, but not with the dot, dot, dot. And get, well, you can do the dot, 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 just not immediately. All right, show that you establish the pattern. All right, and then get to O of n. Let me be more explicit about that, right? Like, I told you couldn't just say, here, dot, 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 O of n, like I did. But what you should do is you should step it once or twice. That's what unrolling means, okay? Unroll this definition like once or twice or three times. Demonstrate that you realize, oh, I'm getting a C sub 1 per step. And then there are n steps. Therefore, I get dot, 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 n C sub 1 plus C naught, so on and so forth, okay? Does that make sense? Like, we want to see that you're thinking and not just consulting a table, because, by the way, this is very memoizable. Like, we literally tomorrow will give you a table where there's many of these recurrences, and then we tell you what the bound is, okay? But we want to know that you know how to solve it, okay? Because these things get more tough, especially if you go and take, like, 15.210, 15.451. These get a lot more complicated, okay? You ever taken the square root of a square root? I remember that one. Okay, so simplify it into a closed form, all right? And then you have a bound. And then you should be done. Okay, this step should not be hard. So really the hardest part is this part. Step 2, write the recurrence. Okay. Sorry, actually I take that back. This is the hardest part. Simplifying the recurrence. We're doing unrolling for now. We're going to see a different way of doing it called the tree method in a little bit. Okay. Okay, cool. Let's move on. So remember the rev function? Well, this is them now. This is what we did with rev, right? We decided that we didn't want to deal with this appending nonsense, and we wanted to make it faster. So what did we do? We just pulled it out and made it tail recursive. But we didn't want that because it's less efficient. So let's actually I'm going to qualify that for you now. I'm going to prove to you, how on earth? I'm going to prove to you that it's actually less efficient. All right? So and it has implications for time as well as space, right? Okay, cool. We have these two functions, and we have rev. Let's do the recurrence for rev. And I've actually spoiled what I was going to say next for you. But w sub rev of 0 is C naught. And then w sub rev of n. And then I should also say where n is the length of the input. Maybe I put it in a tag or something. But I can't write this because I don't know how many abstract units it takes to call this function, to call append. You can assume that plus, times, minus takes constant amounts of work, that it's a single constant, but we don't know that for append. Similarly to how you can't use totality of a function unless you prove it, you cannot tell me the abstract units of append until you show it. Okay? So we're going to show it for append. So we take a detour, hold, and then we go to here. All right? So let's do w sub at of 0. But now we have to define what our where is. And does anyone see why this is tricky? Because append takes in a tuple. Takes in one list, takes in two lists, right? It takes in 2 lists at once. But but I want a single number. So what about, okay, let's write this out, where n is the sum of the lengths of the inputs. Do people feel good about that? Should I do this? Because this would be kind of strange, right? Because now my base case is like, my base case for append is now when y's like could be 1 or 2 or 3 or n in length, right? Now I can't say w sub append of 0 really. I mean I can, but like later on I can't like use that in a useful way. So let's actually say n is the length of the left list. Similarly to how when we did the proof on append, we inducted on the left list. Our work is in depending on the left list's length. Okay. So let's do it. All right. If I have 0 as the length of my left list, I'm going to do C naught work, right? And if I have w sub append of an arbitrary length list, I'm going to do what? I'm going to do cons, and I'm going to recursively call myself. So I get w sub append of a list that's 1 less, because x's is 1 less than x cons x's. So n minus 1 plus c sub 1. Someone tell me what this solves to? Yeah, if we dot it, we're going to get n times c sub 1 plus c naught. Don't do this on your homework, but I don't want to bore you in lecture right now. And this is in O of n. Okay? Are we cool with this? Now let's move on. Actually, no, I left myself room up there. Right. So let's go back to rev. Let's pop the stack and go back to where we were. All right, that doesn't make sense to most of you probably, but that's okay. W sub rev on n, now I have append. I know what the, so let's write it out first and then let's simplify, okay? So if I append with rev, well, okay, what am I going to do first? I do a constant amount of work to call the function and return and whatever. So let's say c sub 1. I also do a call to rev, so I'm going to say w sub rev. And, well, what, I need to be able to justify to myself. What's the length of x's? It's n minus 1, right? Because it's 1 less than x cons x's. Okay, now I need to justify it to myself. So append takes in the result of rev of x's. What is the length of rev of x's? N minus 1. I will not require that you prove that, or that you like you can justify it. You should probably say something. But like rev of x's just returns the same list but reversed, so the length is the same, okay? So it's okay to be like w sub rev n minus 1. Append, sorry. And these are pluses. Why did I not like multiply or something here? Would this be okay? Would this make sense? Because like this is kind of a weird thing to say. Like the abstract units I took to perform this computation, I do this one as many times as the abstract units I got out of this computation. Like it kind of doesn't parse. It kind of doesn't type check in your brain. Okay, we add them because why? Eager evaluation. I did rev of x's, I stored the result, and then I did append. Okay, it's a sequential thing. Plus corresponds to sequential operations. Okay, so we have that. All right, and then I will need word space for this. Darn. Okay, let's solve. So, well, first of all, let's replace this. Okay, if I have w append of n minus 1, let's say that this is going to be in abstract units. This guy, right? Because I got this earlier. So let's do, I have them in like a bad order. I'm going to put them like this, okay? N minus 1 plus C1 from here, okay? But this guy I'm going to say is, yeah.
The append and the rev C1 and C0 are different C1.
Yes, that's true. This C1 is that C1. I just moved it over. We will get another C1, but here's what I'm going to do. I'm going to say, I don't care. And I'm going to say N minus 1, yeah, C sub 2, actually. Oh, sorry, I thought you were talking about this guy, which I was decided not to care about. You're correct that this one we're going to say is C1 prime, which looks like a 1 with a superscript of 1. No, I'm not actually going to do that. Let's call it C sub 2, okay? Call it B?
Or does that matter?
No, not at all. Not at all. It doesn't matter what it's called at all. If you call it like I don't know, Diddly Joe from Mexico, like your TA might get a little like upset that your page is now like 50 characters long, but like don't go crazy. So we're going to do this, okay? And then these are, you're correct that these are different. But what I did is I dropped this. Why? Because this is clearly larger than that, right? I don't care if you do that. It makes the notation a little bit simpler. If the shortcuts I'm taking are confusing, please speak up. We can do it in more detail, but I'm trying to like show you that like you don't have to do as much work later on when you're solving this for yourself, okay? Because it will take effort. All right, so we're going to do this. Is everyone on board of why this is that? Because we got a constant, which is different, and it's n minus 1 because that was the size of our input, okay? All right, so now we have, let's just say that this is that, right? This is that. And then let's solve. Let's unroll. So we're going to get, this is now on n minus 1. So what do you think about this? What do you think about this? Does this look OK? I substituted this for that, basically, is what I tried to do. Does anyone see an issue here? I will erase a pen in the meantime. So there isn't, yeah.
I mean, every red call, you need to also add another, like, append call, so you're not including that?
Sorry, say that again?
Like, every red call, you need to, like, make another call on append, and just doing that, like, I don't think that's doing.
Yes, so it's actually, yeah. We have an issue, because I forgot recursive call. So I need to add in, put it here. But I claim there's actually still an issue here. Yeah. N minus 2. Yep, actually, we'll get 2 touches for that. When I put in n minus 1 here, this is now n minus 1. N is now, it doesn't quite make sense, but like let's say this is like an arbitrary variable k. This is k, and then k is equal to w sub rev of k minus 1. If k is now equal to n minus 1, then this is k minus 1 minus 1. Does that make sense? I'm substituting in n minus 1 for the place of this variable that happens to be named n. Okay? It doesn't matter to me this is named n, but my point is that like we're going down by 1. So this should be n minus 2. Is this confusing to anyone? Does everyone see why that is? Okay. The Haguruma is dying on me. All right. And then let's do another one. Okay, so if I expand this once more, I'll get w sub rev of n minus 3 plus c1 plus, wait. Yeah. Plus c1 n minus 3, c2 plus, actually, no, I'm not going to write that. Never mind. Okay, so what we notice is that we get an n minus 1, or sorry, an n minus I at the ith step, right? Again, n minus I c sub 2, all right? And let's just collect these c sub 1s, right? So let me actually rearrange it for you. N minus 2 plus c1 plus c1 by taking these two together, right? Plus n minus 2 c sub 2 plus n minus 1 c sub 2, okay? So like these are like and these are like, but I notice I add 1 to it every single time. It's just that this depends on my n. It goes down by 1 each time. So what am I going to get? I claim to you, and stop me if this doesn't make sense, if you dot it, what you're going to get, you get the sum from I equals 1 to n of n minus I c sub 2 plus n c sub 1 plus c naught. Does this make sense to everyone why we should get this at the end? If I unroll it n times, I'm going to get n of these terms where they all depend on n itself. And then I'm going to get this guy n times. And then I get my base case. Okay? But now this looks kind of gross. I didn't sign up for this. I didn't sign up to do math. Okay? Like, why do I have to now deal with this simplification of that term? And the answer is I don't want to. The answer is I don't want to. So what does this really look like? Well, this expression actually looks like n minus I up until n is 1 plus 2 plus dot 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 plus n c sub 2, right? Plus n c sub 1 plus c naught. Do you see how I got this? Like I expanded out the summation. This is really what this looks like. It's 1 plus 2 plus dot 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 plus n c sub 2. And do I have a fancy math fact about what the sum of the first n natural numbers is? We did a proof about it, kind of, but we did the odd numbers or the even numbers or something. Who has off the top of their head? What is this? What is that quantity? What can I say this is? Oh, yeah. I like it. Fancy guy called Gauss. Once upon a time. Sorry. Cool. So let's say this is, so in general, you can say this, right? You can use this for free. I will not require that you prove it. This is a math fact. We're here to learn programming facts, not math facts. Okay? So this is free. Okay? But this means that our quantity from earlier is going to be n plus 1 over 2 c2 plus n c1 plus c naught. Would anyone like to be so brave as to suggest a complexity bound for me here? I heard n squared, yes. Because you have an n times n here. Yeah, doesn't matter, it'll be divided by 2. OK, after a page of equations, we come to conclude that rev is quadratic. I promised this to you already, but now we've proven it. I've shown you, you don't need to think about what's happening here because you did the math. Because we stated these, and this is like a very positive, this is a point in favor of like modus ponens, of like implication. Like we stated this, and you agreed with me that this is the recurrence, and it was very easy to state. And then I stated this, the append recurrence I erased, and we stated it was very easy, and we agreed. And now we solve it, and pages of math later, we get this. So we must be correct if the recurrence was correct. Okay? Recursion is a way of stating an infinite amount of information in a finite amount of space. Okay? Yeah. So which step are you saying would become the lied? I'll be wary of making that simplification because you might go too far. Like in a different situation, I could see you making that simplification and getting not as tight of a bound. I'd prefer that you go from here to there. You're correct that in this instance, it doesn't matter. You get n squared either way. But I'm cautioning you that like in general, like making substitutions freely of, oh, this is less than that, so let me replace it with that, leads you to like get worse bounds than what you could otherwise get. So I'd encourage you to please do this. Yeah, OK. OK. I hear chatter, so does anyone have questions? Are people? Oh, yes, plenty of people. Yeah. There can be. I can't recall in this class whether or not that's true. It might be 210. But it could definitely be. Yes. Yeah. If you come out with constant multiples and constant additions. Yeah, that's perfectly fine. As long as we picked this because it was the biggest quantity. Yeah. Yeah. This thing. OK, yeah. So if we look at the code here, rev makes a rev makes a call to rev on a list of length n minus 1. So that's where the w sub rev of n minus 1 comes from. And the c1 comes because we have to do like some constant amount of work to like make the singleton x, to like return. There's always a constant amount of work. Yeah, some constant we don't care what. So yeah, it exists. OK, yeah. This to that, the yellow stuff. Oh, this to that. OK. So I took this, and I put it there. I took this, and I put it there. And I took the w sub append, and I erased the recurrence for you. But if you remember, it came out to be n times c sub 2 plus like a c naught that we don't care about. This is n minus 1, not n. So we get n minus 1 multiplied by a new constant c sub 2, because append's constant is not the same as this one. Sorry, I erased the recurrence so you can't see it anymore. But if you go back to the notes, you'll see. Yeah. OK. All right, we're going to move on because I have not that much time. But this is basically everything I just said. Everything I just said, but worked out. So you can refer back to this if you're confused. OK. Blah 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 blah, so on and so forth. And then if we went to go analyze t-rev, I'm not going to write this to you. For you, but I'm going to tell you that this will end up being linear because we will get exactly the same recurrence that we got for like length or for a fact. Okay, because we do constant, and in the recursive case, we do a constant amount of work plus a recursive call on a list of length n minus 1. Okay, and the work for that is in the textbook, and by the textbook I mean my slides. Okay, all right, but we're going to move on. Okay. So I wanted to just kind of say like the reason why we can do this is because our functions are pure. Okay, given something of the same size, I always get predictable behavior, agnostic to like hardware-specific things, like how long does it take to add two numbers where one number is like really big. Okay, so this comes directly out of our purity property. Okay. So claim to you functional programs help us reason about our code. I think I have a question break now. Yeah, okay. I wanted to take any questions, and I also wanted to do something where I noticed that the same people are asking questions, and I don't really like that because I feel like it's not because the same people of you are confused. So I have this website here. If you go to it with that code, you can ask a question anonymously. And I will otherwise take questions that anyone else has. Does anyone have any other questions right now that I can answer while we wait? Because I know stuff can get confusing, but we're going to work through it. Okay. The point of like being able to do these recurrences is, again, like this idea that programmatic thinking and mathematical thinking are the same thing. Okay? You write your program, you get the proof. You write your program, you get the recurrence. Recursion helps us. Finite amount of space, infinite amount of math facts. Yeah. Always able to, like, for an arbitrary function. For some recurrences, this is a really esoteric quantity. Like, it's like kind of strange. Like when the thing you decide to recurse on is something that's not clear. It's not just the length. It's not just the number. It's like a relationship between the numbers sometimes. So like, I would say that it is not always. That's like a philosophy of math question. Like, is it always solvable? In the class, yes. But in general, it could be a hard question. Okay, I'm gonna go check Menti now. Jesus Christ. All right. Okay. All right. All right. No Menti for you anymore. Cool. Okay. We're gonna move on. Wait. Is that a question? Jesus Christ. This is my first time using this. All right. Thank you. All right. This is the thing. This is a comedy club. I'm not paid to have you laugh. Straight faces. Stop smiling. All right. Quiz time. Let's go. Stand up. House Blue team here. Please actually do this. You need the help. Come on. Help me help you. House Blue team here. I'm telling you, you need the help for this quiz. All right. Let's get going. How's everyone feel? Thumbs up, thumbs down. I realized there was a math fact that I didn't actually like show you, so we might not grade that one. Actually, don't grade the one about 1 plus through n. 2 plus 4. Yeah. Thanks. I thought I told you that math fact already. I did not. All right. Cool. It's O of n. It's bounded by 2n. I'm going to show you why that is. Yes, okay. Let's move on. All right. We're going to talk about parallelism and span. I told you something about how functional programs are like kitchens where the cooks can never mess with each other. Functional programs, hey, pipe down now. Functional programs are inherently thread safe. They're inherently parallel friendly. And I'm going to claim to you that we're going to be able to see how that's true also in terms of how they run in parallel. Okay? So, we talked about work, which is how we measure the cost of a computation in abstract units, like this, right? But it's not necessarily true that this computation needs to take 3 steps, because I just did this one, and I just did that one, and I did this one. But if you think about it, a really smart computer could somehow manage to do 2 of these at the same time. Okay? So this idea of parallelism, I'm going to claim to you here. Let's have a race. I want a volunteer from the audience. You're going to race me. You're the only one raising your hand, so yeah, come up here. All right.
Go. Wait, I have to go up?
Yes, come up here. Come up
Okay.
in front. We're going to have a race, okay? So here's what we're going to do. We're going to race to see who can count the number of people in the room fastest.
Huh?
Yes. Okay? No, don't start yet. All right, keep your head turned. All right? Okay, ready? 3, 2, 1, go. Nancy, come up here. Help me out. Help me out. Hurry up, hurry up, hurry up. No. Keep counting. 1, 2, 3. You take the left half, Nancy. 1, 2, 3. What do you get? Okay, 58. No, 48. Okay, I get it. That's the classic demonstration thought of by Rob Simmons. I want to say, no, not Rob Simmons. But Mike Erdman told me about it. Basically, if we had been on the same page fast enough, then I could have counted the right half, and then she could have counted the left half, and we just sum up the answers. Okay? Counting is a parallel friendly operation. So the point is that, okay, if we were working in like computers and then we had like RAM and disks and a memory and multiple cores, this would have been a faster computation to do if we divide it in half. Okay? That's the idea. So we can use parallelism to solve some problems. And that's the idea of parallelism, when a process can execute some tasks at the same time. When I can do multiple things concurrently, then I can get a speed up on some problems, but not necessarily all problems. Okay? The hardware level of it is, like a processor delegates instructions to different cores, and then they do them at the same time, but we're going to forget about that because we don't care. Okay? Processors exist. That's good enough for us. But it's hard to pick a number for how many processors we have, so we're going to assume we have an infinite amount. I'm not joking with you here. We're going to assume that we have infinitely many processors. And you might be thinking, like, infinite processors, shouldn't we be able to do literally any computation? Well, that's not true, okay? Because even if I had infinite processors, I can't necessarily always make use of parallelism. Parallelism is specific to the algorithm and specific to the code. Consider the problem of making a sandwich, okay? If I want to make a sandwich, if there were an infinite amount of me, all right, I might want an infinite amount of sandwiches. But making a sandwich is kind of a hard process, right? If I want to make a sandwich, I gotta I gotta chop the bread. I gotta put mayo on the ham or whatever. I gotta get a slice of cheese from the fridge. I have to do a bunch of things. Maybe I have to put it in the pan and toast the bread. And even if there's an infinite amount of me, what we're going to do is we're going to crowd around the same pan, and we're going to get in each other's ways, and we might fight at each other or something. So it's not necessarily true that I can instantly make a sandwich. So the note to you is that making a sandwich is hard. It's a hard problem. And this is the idea, this is an analogy, I know, crazy, of task dependency in parallel computing. Certain tasks depend on other tasks, and we can qualify that. Some tasks have dependencies, meaning you can't do them until you finish other tasks. Okay? So here's a graph for you here, okay? If I want to assemble the sandwich, first I got to toast the bread in the pan, but before I can toast the bread in the pan, I got to heat the pan, and then I got to slice the bread. But also before I assemble the sandwich, I got to get the slices of ham and the slices of cheese. In this analogy, I'm making a ham and cheese sandwich, okay? So the question of how long does it take to make a sandwich, which you're all wondering now, the answer to that is the length of the longest path. The longest path among these operations is however long it takes me. It's not necessarily this one, because I might want really premium cheese from down the road. Okay, I want to go to Jiegl and get my cheese. So I got to take a 61A down to Murray, Forbes and Murray and get that. Okay, so this might be the longest step. But this might be also. It depends on how long each step takes. So the longest wait time among all of these prerequisites is how long it takes me to build the sandwich, even if I was parallel, right? Because I might have 3 of me doing these steps while I'm doing this one, but because the 61A was delayed and my bus card doesn't work because I graduated, then I can't make the sandwich, okay? So that's the analogy you should have in your head, okay? So this is the idea of a task dependency graph. This is not super important to know. Just have the idea in your head that a task dependency graph, we can write a graph that shows the dependency between tasks, and the idea is that the longest path through that graph is the cost, okay? If I have a graph, like a general task dependency tree or graph or whatever, if I have one processor, I can't avoid doing everything, okay? If I have one processor, I can't avoid having to heat the pan and slice the bread and get the slice of ham and do this all sequentially. But if I have many processors, I can do it from top down, okay? That's the idea of parallel computing. Okay. So this is the difference between what I'll call work and span, okay? If I have the work of a process, work is how much it takes me to do it using one processor, and span is how long it takes me using infinitely many processors, okay? Here's a thing you should know now, okay? We said earlier that tuples are evaluated from left to right. From now on, when we're doing span calculations, you can only when we're doing span, right, when we assume we have infinitely many processors, you can assume that tuples are evaluated in parallel. That means that if I have E1, comma E2, both of these are done at the same time. So to step something like 1 plus 2 plus 3 plus 4, if I'm talking about span, if I assume I'm in that case, this might be one step, because I can do them independently, because the arguments to plus are a tuple, okay? So that's the idea. Only when we have tuples. Only tuples can be parallel, okay? We use recurrences labeled with W for work. From now on, or span, well, not from now on, but when we're doing span recurrences, they will be labeled with S, okay? So let's do the span. In fact, let me check how much time I have. Let's do the span of the length function, okay? It's going to look very similar. I already told this to you, okay? Let's do the span of length. So same thing, where n is the length of the input list. I want two equations. I want S sub 0, the span on a list of length 0, sorry, S sub length of 0, and this is still C naught, right? It's still constant, even if I have infinitely many processors. And what you should think is that when I put S, I'm now in my span brain. I'm thinking about as if I was holding infinitely many processors, except I can't actually physically do that. And then I have S sub length of n. Well, OK, let me think. If I had infinitely many processors, I could do the computation of 1, the value, and I could do this length of x's call at the same time. Okay? So I'm going to say that the amount of work I have is the max of C1, and then S sub length of n minus 1. It's the maximum, right? Because these happen at the same time. It's the time it takes me to do the computation of my arguments is the length of the longest path. And then plus C sub 2. But if we look at this, clearly the maximum of these should be the length, right? So then I get that the maximum is just S sub length n minus 1 plus C sub 2. If you swap out the S for W, we already saw this recurrence. Right? This is the linear length recurrence. This is the O of n. I'll leave this as an exercise to you. Okay? What gives? Why? I promise you infinite power. I promise you infinite processors. But we got the same bound as the work. Why? Yeah. Right. If two processors take over the 1 and the length of x's, a third processor still got to wait for them to do the plus. That's absolutely true. So we say that for a function on lists, it's inherently sequential. A list is an inherently sequential data structure. Okay? So when we're doing this, we're not going to expect to get a better span bound when we're doing stuff on lists. Okay? That's a general rule. Okay? So if we do all the math, we do all this out, blah, 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 we're going to get O of n. OK. I know I'm skipping through these, but just listen to my words. Okay. What's a data structure that has more than one child? If I have a list x cons x's, if I recurse on x's, I still have to wait. Like I can only if you visualize a list like this, right? X cons y cons z cons x's. Before I get here, I have to look at this. Before I get here, I have to look at this. Before I get here, I have to look at this. Sequential, right? But there's a data structure where we don't have that problem. It's called a tree, right? So if I want to do parallel operations, let's try doing it on a tree. I got tree sum for you. Let's try to do it. Okay. Here, okay. So actually, I shouldn't skip ahead. The first step: define your size metric. What is the size metric for a function on trees? How do we quantify the size of a tree? So we say where n is. Does anyone have any ideas? I heard multiple people say, I think, number of nodes, right? Okay. N is the number of nodes in the input. Okay. Let's do that. Well, if I look at tree sum, I get S sub tree sum of 0 is C naught, and then S sub tree sum of n is, well, OK. Now I have to be able to say something about my recursive calls. But how many nodes are in the left and right subtrees? For an arbitrary tree, I don't know. Right? I don't know how many there are. But remember, life lesson, be pessimistic. So what's the worst case behavior? What's the worst case for us, you think? For if it's a spine, if it's just a singular line of nodes, right? So, and also, by the way, there's two options here. We could have done the number of nodes or the height of the tree, and we'll do the height of the tree next lecture. Okay. So let's be pessimistic. So what I'm going to do is I'm going to say that we have an unbalanced tree. Okay. If I have an unbalanced tree, if I'm doing this, let's say that all the nodes are on the left. Okay. I'm going to have S sub tree sum. And actually, let me not forget the max. Okay. It's the max over, and I'm going to make it max n-ary. But S sub tree sum of my left, which is going to have n minus 1 nodes in it, and then a constant amount to do tree. OK, actually, no, I'll write this down. S sub tree sum on 0, and then some constant amount of work plus C sub 2. Is everyone cool with this? I'm doing all of them in parallel. I'm computing the x. I'm computing the right and the left. But this is my right, and this is my left for an unbalanced tree, because it looks like this. Yes? Computing the set. That's for the additions afterwards.
Oh, okay.
The C sub 2. Yeah. Everyone cool with this? So if this is true, well, clearly the maximum should be the S sub tree sum n minus 1. n minus 1 plus C2. Again, this is the same recurrence if you ignore the name and you ignore the S, right? Do you believe me that this should solve to O of n? What gives? I first promised you parallelism, and then I promised you parallelism on trees, and then we got none. Our bound was not good. If I look at a tree that looks like this, it's really just a list. It's a list that's pretending it's a tree, but it's a list nonetheless, okay? If I have unbalanced trees, I'm not going to be able to give you better bounds. So let's do better, okay? There's a lot of skipping through what I was going to talk about because I already said it, okay? So here's the idea. Yes, okay. So there are only really two cases for trees. Either it's unbalanced, which means it looks like this, or it's like a full tree, okay? A complete tree. And in the case where it's a complete tree, a balanced tree, we're going to get a better bound. So now assume that we have a balanced tree, which looks like this, okay? Here's what I'm going to do. So I'm going to say that the balanced case looks like this. We're going to do S sub tree sum of 0 equals C naught, and then S sub tree sum. Well, what do I say now? I'm going to get, oh, geez, okay. I'm going to get this. I thought it would show me the function again. S sub tree sum. But the number of nodes in my left subtree for a balanced tree is roughly half of the amount I had initially, right? So max of n over 2, and then also we get a C sub 1, and then we get an S sub tree sum of n over 2 plus C sub 2, okay? And if you believe me, the maximum of these we don't actually really care. So we'll get S sub tree sum of n over 2 plus C sub 2. This makes sense to everyone? And now we're going to look at the math fact that I told you about in the quiz, which is that this thing, if we expand it, is going to be S sub tree sum n over 4 plus C sub 2 plus C sub 2, right? Equals S sub tree sum n over 8 plus C2 plus C2 plus C2. So now, instead of getting a C2 every time, rather, instead of doing it n times, right, we're going to keep dividing by 2 until we no longer can. What's another word for dividing by 2 until you no longer can? Taking the log, right? So what we're going to find is that this, if you dot it out, solves to log, I suppose 2, but you know, it asymptotically doesn't actually really matter. If you just write log 2, well, log n, we'll be fine with that. C dot C2 plus C naught. And that's because of this base case, right? So is everyone clear, cool with like this? So we get logarithmically as much time because of this, okay? We get to do a better bound because of parallelism. I feel like I'm running out of time. Yeah. Okay. And you should believe me here also because if I am doing this, like this is, think of this as the task dependency graph. This basically is, right? To do this, I depend on that. To do this, I depend on that. So if I had infinitely many processors, I go and I do this, and then those processors are like, hey dudes, like take over these guys, and then do them, and then they're all being done in parallel. So really, like the amount of work it takes me is the height of the tree, which is log n. If you know anything about complete binary trees, the height of the tree is the log of the number of nodes if it's a complete tree. Okay. Okay. So we get a better bound. And then we can see that parallelism does help. Okay. Oh, it turns out actually the math fact I gave you in the quiz is actually not even for this lecture. Okay, cool. Next lecture, you'll see. Okay. I have to say this because we always have to say this, but yes, infinitely many processors is impossible. We can't do that. Okay. We can have 4 processors. We can have 8 processors. Somewhere out there is like someone with 32. I don't even know if someone knows the maximum amount of that. But it's impossible. But that doesn't mean that this is useless, okay? We mathematically proved the behavior of how what our bound was if we had infinitely many. But the idea is that in reality, the actual cost falls somewhere in between. So the actual cost of using tree sum falls between linear and log. There's a theorem called Brent's theorem that goes more into this. I omitted it from this slide. But it's somewhere between, okay? So this is not useless, okay? But we can analyze how fast our machines run even with parallelism. Okay, that's the idea. All right. And yes, I knew this the whole time.